Good evening, YouTube. In this video, I'm going to be discussing some very basic differences between alternating current and direct current arc lamps. Here before us, we have an Adams Bagnall arc lamp with a indoor ornate shade and the enclosing globe. Typically for indoor applications, this would be opalescent or milk glass. However, it's really hard to see what's going on if you can't see through it. So I'm using clear enclosing globes just so you can see it. So we've got this wonderful streaked, oxidized, factory finished lamp right here. And then over here we have another streaked, oxidized Adams Bagnall lamp. So looking on the outside, one's got all the glass hardware, the other one does not. So these are both the same, right? Well, if you open them up, they're going to be very, very different on the inside. So we'll take a look at the inside of these two arc lamps and see what's going on inside. So we've got the nice, cute little label there, and we'll open the door here and see what is to be seen inside of this particular Adams Bagnall lamp. Now, these are later generation fixtures, so a majority of the AV lamps that you're going to encounter, they're not going to have any kind of labels inside the door. But in this particular label, it says DC multiple. The line voltage is 220 volts. The arc voltage is 150 and runs at 3 amps. So originally, this particular arc lamp was designed for 220 volts DC. However, I have made some adjustments on it so that it'll run on 110 volts DC quite fine. On DC Adams Bagnall lamps, and you'll see this on other types of direct current lamps, you're going to have multiple different taps on the resistance coil to change the voltage at the arc. Originally, this was way over here for 220 volts. However, I'm running it on 110, so I moved it over here so that I could run it on 110 volts. And if I was running it on 100 or even 90, something to that effect, I would move it even further over to get the appropriate 72 volts at the arc. I can't really show it too well, but those white things you see on that vented metallic structure on the inside have coils of nichrome wire inside of the white porcelain insulating rings. And for direct current lamps, the only way to limit that current is with a physical resistance. And originally they used iron wire, which is very susceptible to rusting, particularly when it's hot. And nowadays we use nichrome, which, using the same gauge as it's replacing, you pretty much use the exact same distance to get the correct amount of ohms to limit the current at the arc. So in direct current lamps, you're going to have some type of heating material for the resistance, nichrome, some type of wire wound resistance. And then also on the solenoid plunger assembly, which is this thing I'm pointing to, it's going to be solid and metal. This whole thing that goes into the lifting coils that I'm moving right here, that solenoid lifting mechanism is going to be solid and metal. And aside from that, everything else is going to be the same, because on direct current and alternating current, electricity sort of functions the same as far as the circuit goes, but the magnetic fields are going to be a little bit different. So that's the direct current model. Like I said earlier, this particular one does have a label. There is a 90% chance, 99% chance of whatever arc lamp you're going to encounter is not going to have that nice little label. So here's our other Adams Bagnall lamp. These are from virtually the same time period. The label's the same. The outside is the same. There's really no physical difference from the outside that would indicate that one is an alternating current and one is a direct current lamp. So let's open this one up and take a look at the inside. So last thing I showed you on the direct current lamp was the solenoid lifting coils. If you look on the alternating current models, they're going to be made of laminated sheets. This lifting assembly is actually multiple laminated sheets of metal that are riveted together. I'm trying to capture that with my camera. You can kind of see the layers there. The reason they use those laminated sheets is to reduce the eddy currents, which reduces the amount of heat that the core of the inductor heats up. And then also on your alternating current lamps, you're going to have a big metal reactor that uses inductive reactance to resist the flow of the alternating current. Here's an Adams Bagnall inductive reactor that I had to fix because somebody ran it on 60 hertz when it was designed for 233. And although the lamp kind of worked, it just melted the varnish and the insulation off the coils, and I was able to rewind that and repair that. So while I am talking about frequency and hertz on these arc lamps, if we check the label on here, this particular unit, originally from the factory, was made for 110 volts, 75 volts at the arc, running at 7 amps at cycles. This is the same thing as hertz, frequency, 133 hertz. What that means is this little inductive reactor is wound for 110 volts at 133 cycles per second, or hertz, or frequency, whatever you want to call it. And the windings are going to be different. So even though when this arc lamp is plugged in to 60 hertz at 120 volts, 110 volts, whatever, it might run and it'll, seem like it runs okay. Over time, about 10 to 15 minutes, the inductive reactor is going to get very hot. So, with that being said, on alternating current lamps, unless they're specifically indicated to be wound for 60 hertz, this device is not meant to run on 60 hertz without irreparable, expensive, traumatizing damage. If I run this lamp for more than about 10 to 15 minutes, that inductor gets so hot that I can't touch it with my hand without burning myself, and I am literally fucking it up. I am damaging it, and so many people, and unless you have an extensive background in electrical engineering, so many people don't realize this device, even though I plug it in, it might run for a few minutes just fine, is not designed to run on 60 hertz, and it will damage it if I run it for an extended period of time, because the inductive reactor, that thing that limits the current, will get too hot and it will physically burn up and start melting and burning the windings off of it. All right, so with that being said, now that we know the engineering ins and outs of these wonderful arc lamps, I'm going to shut the alternating current model here, and I'm going to turn it on, and then I'm also going to take our direct current model and also power it up so you can hear and to a certain extent see the differences in operational principles on direct current and alternating current arc lamps. So here is our lovely 110 volts, 133 hertz Adams Bagnall arc lamp that is incorrectly operating at 60 hertz. And I do have the enclosing globe off for a specific reason, and this is going to show you what an alternating current arc lamp would be like when it is operating. All right, so we're gonna turn all the lights down in 3, 2, 1. Okay, so you can hear that 60 hertz hum. It's flickering. The light source is not very stable. It's not very pleasant. But with that being said, alternating current arc lamps did have a very viable purpose and specific application for lighting purposes during their time period. Number one, DC current can't be transmitted for very long distances. So with an alternating current system, you could put some of these arc lamps in series and get maybe 2 or 3 miles without any type of loss on your system. So alternating current at higher frequencies was very appropriate towards arc lighting. You get a little bit closer, hear that 60 hertz hum. You kind of see the arc flickering. Okay. On alternating current arc lamps, also want to point out that you are most likely wanting to use cord carbons. And what do I mean by a cord carbon? A cord carbon has a small inner portion of the carbon that is doped with metallic salts. These are lithium, cesium, basically metallic salts that when they are vaporized into the arc stream, they produce even more light into the arc. And the technology is not too dissimilar to what you would find in a metal halide lamp of today. Those metallic salts are doped into the carbon. And the reason you want that in an alternating current lamp, because the arc is changing direction per se 120 times on a 60 hertz circuit, 120 times per second. There's a little bit of metallic vapor in the arc stream that can strike that arc a little bit better, and it makes it a little bit easier for the alternating current arc lamp to run. So with that being said, in the field and in practice, an alternating current lamp would be 133 hertz, 166, 233. And this 60 hertz hum you hear wouldn't be a 60 hertz hum. It would be double, triple, quadruple that, and it would be a lot higher pitched. The flickering wouldn't be there, and you probably could hear it because it would be so much higher pitched. So there we go. That's our alternating current arc lamp running right there. That gives you an idea of what it sounds like and the operating principles behind it. You can unplug it. You can see both the carbons are red. The top one's a little bit hotter due to convection. And if you look carefully on this label, that is a projector cord carbon. And what that means by that is I bought this off of eBay, and a projector cord carbon means that it is doped with those metallic salts to increase the light output and also help the arc stream be a little bit more stable. So looking over here, here is our direct current Adams Bagnall lamp. And got my ear really close to these red hot carbons over here. It's making me kind of nervous. So what I'm going to do here is get the plug started on my 120 volt DC power supply, and then turn the light off, and we can see this thing start. Hopefully I won't electrocute or burn myself in the process. All right, so here we go. And of course, okay. I don't see any flickering aside from the arc mechanism trying to stabilize itself. It's quiet. No obnoxious 60 hertz hum. That's a DC arc lamp for you. A lot better. If I had a opulent, luxurious department store or a palatial house, I would want a DC carbon arc lamp system in my house. I mean, they're more simplistic, they're quiet, they don't flicker. You can see the light output there, it's nice and white. Point I'm trying to make is AC was more appropriate towards street lighting, arc lighting, and DC was more applicable towards inside arc lighting. A lot of people, when they see DC arc lamp, they're totally, oh my God, they're scared to death because they don't quite understand the power supply. So I'm going to take a brief little second here and we'll look at my power supply. I built this off of parts I got on eBay. It's basically a electrical junction box that I bought here. I think it was $60. And then just for some shits and giggles, I got some electrical meters here with appropriate parameters so I could see what's going on. So this particular lamp's operating about 117 volts and about, I don't know, 3 amps or something at the arc, nothing too crazy. And then where the real magic happens is inside of this thing, I got 1, 2, 3, 4, 5, 24 volt direct current power supplies, and I wired the secondaries. See all those little wires jumped up there? I wired the secondaries in series to get 120 volts DC out, and then the primary or input side, those are in parallel, so each power supply gets 120 volts alternating current, and then the secondaries take that 24 volts times it by 5, so I get 120 volts direct current out. Here's the plug right there, and there's the terminal leads that output the 120 volts of DC, and then there's a hole I cut in there to put a fan in there, but this thing is so underutilized that it doesn't really need a fan. Each one of these power supplies will output 20 amps of direct current. However, due to the fact that they are in series, they're only outputting 3, which is well below the threshold of what these things can output. They are bolted to the back of the chassis here to keep the heat sinks pressed against the large metallic surface to try to dissipate the heat. And then here's all the electrical gauges, which I have wired up to indicate what this thing is outputting. Overall, those little 24 volt DC power supplies I think cost me $180 on Amazon. Chassis was $60, and then these silly little gauges, which you don't really need, but I wanted to put on there to be cool, cost me, I don't know, about $300 for this power supply. A lot of people use solid state bridged rectifiers, which there's a reason I don't really like those. And mainly, it has to do with the fact that if you were to take an oscilloscope on a solid state bridged rectifier, so the solid state bridged rectifier looks like this. It's got your diodes on it, and what it does is it takes here's your alternating current on an oscilloscope. This is what the sine wave would look like. And what the solid state bridge rectifier does is it takes the sine wave here and then clips all of the other portion and basically makes your so-called direct current wave look like this, which I don't really like that, because if you look on other videos where somebody's running a DC device on a solid state bridge rectifier, you can hear it hissing. It's going bing, which is where the sine wave dips down like that. It doesn't sound right. The lamps chatter, and this isn't direct current. That's alternating current with the sine wave on one side. It's not direct current. Direct current on a oscilloscope is going to look like this. It's going to be a pure sine wave. Everything's going to be flat, and that dramatically affects the way the arc lamp runs. It doesn't chatter. It doesn't hiss. This is how this thing was intended to run. Completely silent. You know, completely silent, no chattering at all. That's how the lamp was designed to run. So anyway, I appreciate you sitting through this video. 20 minutes of me running my mouth about a bunch of obscure, goofy-ass antique technology. And I hope you did find this kind of informational and informative, because there aren't any videos really discussing the technology or the theory behind these things, and I find these arc lamps utterly fascinating. So until next time, I'll see you later. Bye-bye.